Good morning, afternoon, evening, whatever it is for you. Today we are there we go. Sorry, this is chapter 7.2. We are talking about the nature of earthquakes. And we'll talk a little bit, well, when we get done, you should be able to use models, diagrams, and captions to explain how tectonic motion creates earthquakes and tsunamis. Using resources such as indianamap.org, analyze how close the school is to known faults and liquefaction potential, and differentiate between intraplate fault zones such as the Wabash Valley Fault System and the more commonly discussed faults along tectonic margins. By the time we get done today, in particular, you should be able to identify an earthquake focus and its epicenter, identify earthquake zones and what makes some regions prone to earthquakes, compare the characteristics of the different types of seismic waves, and describe how tsunamis are caused by earthquakes. So you need to remember that an earthquake is the sudden ground movement caused when there's a sudden release of energy stored in rocks. We've already talked a little bit about this. We just didn't go into a lot of detail. Remember when the ground moves at those plate boundaries especially, that energy stores up. And the stress in the rocks build up so much that finally that rock will rupture. It'll break and it releases a lot of energy. That energy is transmitted through the earth in something called seismic waves. Now, we've already talked about that, so hopefully you're remembering that. Elastic rebound theory is what describes what happens building up to an earthquake. Basically, it says that as this earthquake is moving on both sides of a fault, remember a fault is just a crack in the earth, as stresses build up on both sides of that fault, it causes plastic deformation. Remember that plastic deformation, once it deforms, it doesn't go back to its original state. So if you look here, here's what the fault line looks like to begin with. At time 2, you can see that this side has moved up, this side has moved down, and it's plastically deforming it. It's pulling it and pulling it and pulling it until finally at time 3, there is that break. And now these two are in a totally different place. So the stress is going to build and build and build until the rock actually breaks and ends up in a different area. It is that movement, that breaking, that causes an earthquake. As that ground moves and breaks apart, it causes an earthquake. So the focus of an earthquake is under the surface. This is where the rocks actually rupture. Usually they are between 6 and 9 miles underground. These are not going to be up at the surface. Most of the time, we aren't going to feel the focus. The epicenter is the point on the surface straight above the focus. So if there's an earthquake that happens down here, straight up above that is the epicenter, and this is where we will feel the earthquake. This is where we will feel the earthquake. Epicenter is what is reported by scientists and media. We can't report the focus because it's down underground. About 95% of all the earthquakes occur at convergent, divergent, and transform boundaries. Remember, convergent boundaries are where plates come together. Divergent boundaries are where plates move apart. Transform plate boundaries are where they slide past each other. 80% of those earthquakes happen around the Pacific Ocean basin in the area known as the Pacific Ring of Fire. Remember, we've talked about that already. it goes all the way around the Pacific Ocean. 15% of that 95% occur in the Mediterranean Asiatic belt. Guys, that only leaves 5% of earthquakes. Oh, apparently I have two slides of the exact same thing. I apologize for that. Here's the Pacific Ocean. You notice that almost all, it comes around here and continues over here. This is all Pacific Ocean basin. Notice that almost all the earthquakes happen in that area. There are some here in the Mediterranean area. This is the second highest. And then there are others a little bit of everywhere else. But again, that leaves about 5% of earthquakes occurring at other plate boundaries, like here, or at intraplate locations. There are a few that occur like in this area, and you notice there are some over here. You can find lots more information about the numbers and magnitudes of these earthquakes if you go to your Flex book. I'm not going to go over all of those. They give you a lot of magnitudes and dates for when those occurred and things like that. So the last thing that we need to talk about, the last kind of plate activity that we need to talk about is this intraplate activity. Intraplate just means that these are slabs that move along faults, but the faults are not at a plate boundary. Remember, a fault is just a crack in the earth. That's all it is. So if we have a fault that occurs like in southern Indiana, for instance, then it would be an intraplate boundary. Indiana is actually close to several of these seismic zones. The closest one is called the Wabash Valley fault zone or fault system. It is southeast Illinois. Here's Illinois. Here's Indiana. This yellow line is our borders. And down here's Kentucky. We have Missouri and Tennessee and Arkansas, and you can see all of those. The Wabash Valley seismic zone is southern Indiana, southwestern Indiana, and southeastern Illinois. You notice there are also St. Genevieve seismic zone and the New Madrid seismic zone. A lot of scientists believe that these are kind of all three kind of the same seismic zone, but because there is space in between them, they're actually calling them different ones. It is an active fault zone. Earthquakes range from 3.5 to 7.5 on the Richter scale. 3.5 is when we can kind of start to feel the little rumbly. Anything below a 3.5 we don't usually feel. 7.5, you're getting to a really strong earthquake. There have been 7.5 earthquakes here in the Wabash Valley seismic zone. The most recent earthquake was in 2008 in this zone. It was a magnitude of 5.4. There were aftershocks of 4.6 and 4.4 or 4.0. So the 4.0 would have just been kind of just a little bit of a rumble. 5.4, I remember feeling it here in Anderson, even though it didn't occur here, it occurred down here. I remember feeling it up here in Anderson. Seismic waves is how we feel those. They are what carry the energy in an earthquake throughout the earth. This is a good example of a seismic wave, kind of what any wave looks like. They will have a crest, which is a high point. They will have troughs, which are low points. The space from the middle point of the crest to the middle point of the crest, or from the middle point of the trough to the middle point of the trough, is called a wavelength. It is the length of, it's how long that wave is. The height from the center line to the crest is the amplitude. Put the wrong one on there. This is the amplitude from the center point to the crest. Seismology is the study of seismic waves. Kind of makes sense. The scientists that do this study are called seismologists. And there are 4 major kind of waves. P waves, primary waves, remember we've already talked about these, so this should be just a refresher. The P waves and S waves should just be a refresher. Primary waves, P waves, travel through solids, liquids, and gases. They're the fastest of all of them. That's why they're called primary, because they get there first. Primary waves move forward and backward like this as they travel in the direction of the wave. Okay? S waves are secondary waves. They only move through solids. Remember, that's how we know what's going on inside our Earth, is because S waves don't move through liquids or gases. They move perpendicular, so they move up and down to the direction of the wave as they're moving. As the wave is moving this way, these are moving like this in the same direction. P waves and S waves are called body waves because they actually travel down here underneath the Earth. They don't really travel on the surface. So they travel deep underground through the body of the Earth. Now, there is a third kind of wave that is called a surface wave. Surface waves, there are 2 kinds, and they travel on the surface, hence the reason they're called surface waves. They go outward from the epicenter, and they are the slowest of all of the waves. There are 2 kinds of surface waves. We have Love waves and we have Rayleigh waves. Rayleigh waves are the slowest. They're the last ones to get anywhere, but they travel in kind of a rolling wave pattern. So they're really slow. They do damage. I'm not going to say they don't, because surface waves are always going to do damage. But they kind of are nice and slow, and they don't do as much damage as Love waves do. Love waves are way faster than the Rayleigh waves. They also are the most dangerous. They travel in a horizontal fashion. So they move back and forth like this as they're moving away. Horizontal motion that is perpendicular to the direction the wave is traveling. So if the wave is traveling this way, they're going to move this way. Okay? They do the most damage because they are a little bit faster than the Rayleigh waves. So they're moving faster, and they're moving back and forth, which is what's going to tear stuff up. Okay, last thing we have to talk about are tsunamis. Tsunamis are huge, deadly ocean waves that are caused by an earthquake that happens in the ocean. What happens is, way out in the ocean somewhere, there will be an earthquake. That energy from that earthquake will travel in the waves of the ocean, and they really won't look like anything until they start to get close to shore. Well, because they don't have anywhere to go, that energy doesn't have anywhere to go as they're coming closer to shore. They start building really, really high waves. And as you can see, they can be gigantic. They can be huge waves that can do a lot of damage. The largest tsunami occurred on December 26th, the day after Christmas, 2004. It was caused by an earthquake that had a magnitude of 9.2 right off the coast of Indonesia here. About 15 minutes after the earthquake hit, a tsunami wave occurred in Sumatra. Sumatra is going to be a little island. It's not even on this map. But hit in Sumatra, the waves were 33 feet high, destroyed a lot of buildings. By the time they got to Somalia over here, they were only 13 feet high. Still pretty high waves if you think about it, but compared to 33 feet, not nearly as high. They had a lot of deaths as a result of this. About 230,000 people died. There were deaths even as far away here as South Africa. More than 1 million people, in addition to these 230,000 people that died, more than 1 million people lost their homes, and more than that lost their jobs. The problem was they didn't have any warning system because nobody thought that you can't have a large tsunami in the Indian Ocean. The Indian Ocean is too small. There's no, you just can't. You might have a small tsunami, but you're not going to have a large one. Well, now they know that you do and you can. So they've actually put in a warning system similar to what has been in place around the Pacific Ocean. Obviously, the Pacific Ocean has had a warning system a lot longer because it's more active. So they've had more of a warning system that actually we know that actually works. Many people, when they first put this one in, weren't sure that it was going to work. It has, so things are looking better for them. Okay, that's all you have to do today is the Edpuzzle that goes along with this lecture that you just did. Tomorrow you're going to complete the study guide that goes with this. You will have access to the Flexbook just like you always do. You will have access to the notes that look exactly like this, just like you always do, that will help you with the study guide. So please, 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 please use the materials provided. Use your Flexbook, use your notes. Have a great rest of the day. Thanks. Bye.